Hello, we're Group 8 presenting the energy audit for a tile manufacturing facility in Stockton, California. I'm Michelle and I'm here with Hongbu, Bao, and Sung. In this presentation, we'll walk through how the plant uses energy today, the 5 energy efficiency measures we evaluated, and what those measures mean for cost, demand, and carbon emissions. We'll then finish with implementation priorities and the rebates available to support them. For the executive summary, we analyzed electricity, demand, and natural gas using both the monthly bills and the 15-minute interval data. Two systems that were considered the biggest energy users are the compressed air system and the kilns. We modeled 5 measures, which include pressure trim, leak repair, after-hour shutoff, cogged belts on the ball mills, and the kiln exhaust heat recovery. When combined, these measures reduce kilowatt hours by 6.9%, demand by 4.5%, and both annual cost and carbon emissions by roughly 8.5%. This slide shows the decorative tile process, which starts with mix, then mill, shape, dry, glaze, fire, and then package. The extrusion shift runs from about 6 a.m. to 2:30 p.m. The glazing runs longer, from 6 a.m. to about 10:30 p.m., and firing in the kiln is continuous, running for 24/7. This schedule explains what we see in the interval data, which is a strong daytime ramp as production comes online, and a high, steady base load driven by the kilns. We discovered that there are 4 systems which consume the most energy at the facility. First, the kilns and their fans, which consume the majority of the natural gas. Second, the compressed air system, which runs continuously and is sensitive to pressure settings and leak conditions. Third, the ball mill, which use large motors with long run time. And finally, the supporting loads, which include the glazing oven, HVAC, and lighting. All of the measures we selected map directly to these major loads.
Next slide we will talk about electricity and natural gas rates. Based on the view we have here, we can see the facility in North California and the rate schedule for electricity is B19SCCA. And they track in summer month from June 1st to September 30. The peak time will be 4 p.m. to 9 p.m. The rate will be 36 cents per kilowatt hour. And in the park peak, 2 p.m. to 4 p.m. and 9 p.m. to 11 p.m. the rate is 39.87 cents. And the off-peak from 11 p.m. to 2 p.m. the rate is 26.62 cents per kilowatt hour. And the demand in summertime will be $29.76 per kilowatt. And in winter month from October 1st to February 28th, the peak time is 4 p.m. to 9 p.m. The rate is 28 cents per kilowatt hour. And the off-peak time from 9 p.m. to 4 p.m. the rate difference will be 25 cents per kilowatt hour. And super off-peak, they don't have data for that. And the demand for winter month is $22.54 per kilowatt. And the winter month with super off-peak from March 1st to May 31st, we don't have data for that. And natural gas rate, the schedule is GNR1 gas service. And the tier first gas delivery for the first 4,000 tons per month, they charge $1.37 per ton. And tier 2 gas delivery with greater than 4,000 tons per month, the rate could be $1.31 per ton. And they charge for customer charge like $2.14 a day, and some surcharge and tax and some credit and the charge for supplier. So this is a table for electricity and natural gas. And next, the electricity used by month. Look at the chart. We can say in the summertime from 7 to 10, the facility consume more than the rest of the month in the year. And the end of the year, like November and November and December, the year less, they suggest a good opportunity to maintenance window. And if we don't want to maintenance, we should use this window from November to December. And annual electricity consumption is 409,000 kilowatt hour, and energy cost will be $107,000 per year. And the highest yield in August and September around 44 to 46 megawatt per hour, and lowest in December 22 to 25 megawatt hours. And annual demand charge is $49,649 on 2,264 kilowatts month. It's almost half again with the energy spent for a whole year. So the demand is cost a lot for this facility. And the next will be demand profile. The first chart is demand where again with the month, and here we can say every month the demand is almost same. But take a look in the chart of the power again with hour. We can see the max power from 4 a.m. to 16 p.m. to 4 a.m. to 4 p.m. The demand is higher. And from 17 17 mean 5 p.m. until 4 a.m. in the next day of morning. This, the demand is go all the way down, but still have value because of some equipment is still running at the time we don't do production, but the machine is still on it in that time. And look at the chart. Power again of the day, the Monday to Friday, the demand is high, Saturday is lower, and Sunday is the lowest. This means some equipment still running on the off time. So by the day, the action here we start a lock start lower pressure compressor and automation. After our setup, we save energy and save money for facility.
On the natural gas side, we estimate the facility used about 88,956 tons per year, and that's where the majority of our CO2 emission come from. Using the standard emission factor, electricity contribute about 175,000 pounds of CO2 per year, and while natural gas contribute roughly 1.04 million pounds. That means about 86% total emission are thermal. That's why the Q exhaust heat recovery is our main measure as it directly reduce terms, so it cut both cost and carbon at the same time. The electric side measure still matter as they trim kilowatt hours, reduce demand peak, and delivery incremental CO2 reduction. For checking, we recommend a symbol like measurement, reporting, a verification plan, which consists of monthly roll-up of kilowatt-hour in terms, log of compressor leak, pressure change, and Q heat exchanger change for exhaust temperature and flow. So we can confirm that savings are persisting. And the bottom line is gas measure delivery big carbon reduction, and compressor air measure delivery quick, cash, and lower peak. Together, they reduce 8.5% portfolio reduction we showed earlier. And this is the first three measures focused on compressor air, and they are all high value and low effort action. For the energy efficiency measure 1 is the pressure trim. Dropping the header pressure by about 10 psi save roughly 6,100 kilowatt hour and 26.9 kilowatt months, about $2,800 per year. The payback is under 6 months. And energy efficiency measure 2 is fixing about 10% of system leak. That save around 12,200 kilowatt hours and 53.8 kilowatt month for roughly $5,600 per year, depending on how much repair work is needed. The payback range from a few months to under 3 years. And the last one is energy efficiency measure 3 is after our setup, which eliminate off shift air waste that save about 8,960 kilowatt hour and around $3,230 per year, with a payback of about 2 to 7 months. For the energy efficiency measure 4, we look at replacing the existing V-belt on the ball mills with the cork belt. This improves drive efficiency by about 3%. For this facility, that comes out to roughly 847 kilowatt hour per year and about 21 kilowatt month per year, which is worth around $780 annually. With an install cost between $800 and $1,600, the simple payback is 1 to 2 years. This is a good deal at replacement measure, meaning it is the best done when the bells are already due for service.
I will now represent our final engineering measure and the total project summary. Our final measure target is the furnace exhaust heat recovery. Currently, the hot gas leaves the stack air waste. The solution is we propose installing a heat exchanger. Our target is to cool down the exhaust to 120 degrees Celsius. This allows us to recover the heat safely without causing the damage to the stack. So for the impact, this measure saves approximately $15,000 per year in natural gas cost. It reduces the CO2 emission by over 91,000 pounds annually. For the investment, the estimate cost is between $7,000 and $19,000. Because the savings are so high, so the simple payback period is excellent. It's between zero point 0.5 and 1.3 years. Um, this table summarizes the total impact of all five measures combined. For the key reductions, electricity. So we reduce the consumption by 6.9%. For the demand, we lowered peak demand charge by 4.5%. The most importantly is the facility total annual energy cost dropped by 8.5%. This saved roughly $25,000 per year. We also see a margin 8.5% reduction in the total carbon emissions. This proves the project is both profitable and sustainable. For the implementation and funding, to execute this plan, we recommend the following strategy. So the first one is the priority. So start immediately with the furnace heat recovery and the compressed air fixes. They offer the quickest in return on investment. The second is the maintenance. So we must maintain the saving by performing the quarterly leak check and enforcing the strict in shut-off policy during the peak hour from 4 p.m. to 9 p.m. The third one is the funding. So to minimize upfront costs, we recommend using PG&E rebates. So we also suggest on the 0% on-bill financings. This will allow the facility to pay for the upgrade using the monthly saving, keep the cash flow positive. In conclusion, this audit identified a clear path forward by targeting the furnace and compressor, and we can achieve a 8.5% reduction in operating cost. This project improves the facility efficiency, reduce its carbon footprint, and strengthen the bottom line. So thank you for watching. This is our reference page.